Yeah, so please let me know my audibility. We will start. We'll start. We are done with 2 lectures on network analysis for HPCL. Yeah, HPCL. The examination is about to be conducted in coming, I can say 90 days or 3 months or so. The date of the examination is not yet released, but for the same, we are conducting some YouTube free live classes on network analysis, the subject which is very important for electrical guys. Almost 10 questions you'll get, simple subject. Okay, so once this is done, we will go for some other subject also of electrical engineering. In network analysis, again we are done with, yes, again in network analysis we are done with 2 topics, that is first basics, 2 lectures, okay, of 1 topic, that is basics. We are done KVL, KCL, Ohm's law, okay. uh, these applications, nodal analysis, mesh analysis, on these we solve some problems also. So in this class I'm going to, and we saw the combination of resistances, series combination of resistances, parallel combination of resistances, right? In this I'm going to discuss first delta to star, star to delta conversion of star as of resistances, inductance and capacitances, and after that I'm going with the network theorems, DC theorems. Okay, DC theorems. First, see, all of you know how to convert from delta to star or star to delta, but still I take, but here some people have some confusion. Okay, I'm going to remove the confusion from your minds by doing this delta to star and star to delta. Yes, if you have any doubt, you can chat in the you can type in the chat box. Okay, I'm observing your chat box. If you have any question, you can type. Right, ready guys? Yes, delta to star. Yes, delta to star and star to delta conversion. Yeah, delta to star conversion of resistances. Let's take resistances first. Okay, delta to star conversion for star to delta, whatever it is, no problem. Just a minute. Yes, delta to star conversion. Suppose if I'm taking resistances, which are connected in delta. What is a delta connection? So don't depend on the shape of the structure always. What is a delta connection? If you take any element, starting of the element, sorry, ending of the first element is connected to the starting of the next element, means I'm taking a resistance here called RAB. So this RAB, this is point A, this is point B, I'm taking, this is resistance. The ending of resistance RAB is connected to the starting of the next resistance, I can say, that is RBC, and ending of the RBC resistance is connected to the starting of the next resistance, that is RCA. This way you connect, this way if you connect, that connection is said to be a delta connection. Okay, shape is not important, I can say this is also delta connection. Yeah, this is A B, sorry, yeah, A B and this is C. Yes, that is also delta connection. But people will see, sir, how you can say that it is delta connection? If I'm taking this terminal, this terminal, this terminal out, yes, that is a delta connection, obviously. Okay, shape is not important, connection is important, right? Now I want to convert this one. I want to convert. Conversion means electrically both should be same, electrically equivalent. Conversion is different, connection is different. Okay, suppose what I do is, what is connection? I'm going to dismantle all this and I'm going to connect in star shape, that is called as reconnecting in the form of star, reconnection in the form of star. I'm not going to take up any reconnection here, just I'm converting from this delta to star. If I convert this delta to star, yes, I get like this. Yes, this is star connection. Here also shape is not important. This is point A. Yeah, means if you convert here itself, here itself, one element you get here, one element you get here, another element you get here, right? So delta to star, I call this one as RA. Yes, this one as RA. Yes, this one as RB, this one as RC, and this is neutral point. Means if all the resistances, this is RB, please, and RC. If all the resistances one ends are connected together, if all the resistances one ends are connected together, then that is called as a star connection. What is delta connection? If ending of the first resistance is connected to the starting of the next resistance, and that way if you complete the circuit, that is called as delta connection. If all the resistances one end are connected together, and that point which you got is called as star point. The point what you got is called as star point or neutral point. Yes, that is neutral, and this is a star connection, right? Then for you, what is this delta to star? Delta to star means that fellow given RAB, RBC, and RCA is expecting the formula of R. This is expecting the formula of R. Observe here what I'm going to do. Observe here clearly what I'm going to do. RA is equal to, you want RA, right? RA is equal to, what is RA? RA is the resistance that is there between RAB and RCA. RAB and RCA. So RA is equal to product of the connected resistance RAB into RCA by total, that is RAB plus RBC plus RCA. Let's take it as RAB plus RBC plus RCA as some, I can say, M. Okay, for my simplicity purpose. Or let's not take it. Why? Because it may confuse you. If I introduce a new variable, you're going to get confused. Okay, let's not do that. Let's not do that. So this is RA. Then can you tell me RB? See, when you're doing delta to star, see, this is delta connection, star will be in between, you're going to get. That in between element is nothing but a product of the connected branch, connected arms, I can say. See, you want this RB. What are the arms connected to this RB? This side RAB and RBC. So RAB into RBC by, yes, RAB plus RBC plus RCA, right? So can you type this RC? Yes. Can you give me the value of RC? Yes, RC. Yes, I am observing the chat box for your reply. Yes, any one of you? Yes. What is RC? RC, please. Yes, yes. You can type. You can type in the chat box your answer. RBC. Sorry, RC. So RC is very simple. Product of the connected elements, that is RBC into RCA by RAB plus RBC plus RCA. Yes, this is delta to star connection of resistances. The same formula is applicable for inductances also. The same formula is applicable for inductances also. So I can write, yeah, these are the statements of theorems I taken to save our valuable time. Okay, come here. Yeah. So suppose that fellow given inductances like this. Inductances like this. That fellow, this is LAB, this is LBC, this is LCA. So this is A, this is B, this is C. If I want to convert this one into star, yes, I'm going to get LA, this one is LB, this one is LC. So this is neutral, this is point A, this is point B, this is point C. So this is LA, this is LB, this is LC. So LA is equal to product of the connected, I can say, branches. The LA you're getting here, right? The product of the connected branches are what? LAB and LCA. LAB into LCA by LAB plus LBC plus LCA, right? Next, LB is equal to LB is equal to LAB into LBC by LAB plus LBC plus LCA, right? LC is equal to, yes, LBC into LCA by LAB plus LBC plus LCA. That's all. Means That formula is applicable for both inductor as well as resistances. Then what about capacitances? Sir, capacitances is different. Let us discuss after completion of this star to delta also. Okay, let me complete star to delta, then I'll discuss about capacitances. Yes, second one is star to delta conversion. Star to delta means that fellow gives you star connection. Yes, this way many people are confused in this one. Okay, this is A, this is B, this is C. Let me take this one as RA, let me take this one as RB, let me take this one as RC. Now what you want? I want this branch, I want this branch, this resistance, I call it as RAB. Yes, yeah, delta means that one only na. I want this branch, I want, yes, I want this branch, that is RBC, and I want this branch, right, that is RCA. Means I'm going to get a delta like this. Yes, you know how delta looks. Just now we are done with that. Delta to star. This is A, this is B, this is C. Yes, this is RAB, this is RBC, this is RCA. Now I'm writing here, the same is applicable for inductors also. The same is applicable for inductors also. Means just you replace R with L, R with L. Therefore, I'm writing here RAB is equal to, yes, you want this one, na? Sum of the connected resistances. What are the sum of, what are the connected resistance? RA plus RB plus product of the connected resistance RA into RB by opposite resistance. Yes, you see how much simple it is. A lot of people will face confusion in this. I can say delta. Sorry, start to delta. Some of the elements. See, you want here, na, can add those RA and RB. Next, what is RBC? RBC is equal to RB plus RC plus RB RC by opposite is RA. Next one is RCA is equal to, RCA stands for RA plus RC. So RA plus RC plus RA RC by RB, right? So this way we are going to get star to delta. The same is applicable for inductances also. Now when it comes to capacitances, see, I'm taking capacitances in star. Yes, capacitances in star. These are the capacitance in star. Okay, this is A, this is B, this is C, right? Capacitances in star, let me call this one as CA, CB, CC. Now you want a delta, you want a delta connected capacitances. Yes, this formula is same as that of, see, somewhat one relationship we have to get here, that is A, B, C. How to get delta values of capacitances from star is the same as that of delta to star of resistances. Star to delta formulas of capacitances are similar to delta to star of resistances. What is delta to star resistances? Delta to star. So you're going to that is see, you want this one, na? CAB. Yes, CAB. I'm writing here. When you are doing delta to star of resistances, what you was doing, you was connected branches product by total you was taking. Connected branches product by total you are taking. Delta to star of resistances, I repeat, delta to star of resistances is similar to star to delta of capacitances, and delta to star of capacitances is same as that of star to delta of resistances. Now here star to delta of capacitances is same as that of delta to star of resistances. Delta to star resistances means product of the connected elements by total. What are the, see, you want CAB, what are the CA into CB, product of the connected elements by total, CA plus CB plus CC, right? And CBC, yes, this is CBC. What is CBC? What is CBC? Product of the connected element. C in between B and C, yes, what are connected? CB into CC. CB into CC by CA plus CB plus CC. What is CAC? CAC is equal to, yes, CA into CC by CA plus CB plus CC, right? Done? Yes, this way we are going to understand. So that note point also I'll write, that is note star to delta of capacitances formula, capacitances formula, yes, is similar to, is similar to, yes, delta to star of, delta to star of resistances, and vice versa, and vice versa. So this is about delta to star, star to delta conversion. Definitely one question in HPCL examination, definitely, there is no doubt about it. For sure you are going to get one question in your HPCL examination, right? Next, let's go for network theorems. Network theorems. See, what is the purpose of network theorem? To solve a big network, a complex network very easily, we are applying these theorems. So in that, the first theorem what we have to discuss is superposition. Superposition theorem. What this superposition theorem says is, if you take a circuit, like this, I'm taking like this, observe carefully please. Superposition theorem. Yeah, here instead of voltage source, let me take current source, no issues. Yeah, so this is V1, this is I1, this is R1, this is R2, this is R3. My target is current in the branch R3, I3. So my response is I3. Response means output. Yeah, response means output. I am looking for the current I3 which is in the resistance 3 R3. So current in R3, that is I3, is due to, because of this V1 as well as because of this I1. Both sources are contributing for current. Both sources are contributing for the current of I3 in the branch R3. Then what that fellow says is, brother, do one thing. Do not consider this one first. Do not consider this one. Not considering a current source means we have to open circuit it. Please keep it in your mind. Current source, if we are not considering, we have to open it. Voltage source, we are not considering, we have to short it. Because no voltage means zero voltage. Voltage is zero means short circuit. No current means zero current. Current is zero means open circuit. Remember, current is zero in open circuit, voltage is zero in short circuit. Therefore, if you want to nullify, if you want to kill, if you don't want to consider voltage source, short it. Sorry, if you don't want to consider current source, you open it, make it open circuit. So I3 in branch current, see the current in branch 3, R3, that is due to both V1, due to both V1 and I1, right? So what that fellow says is I3 is equal to I3 dash plus I3 double dash, where I3 dash is equal to I3 when only V1 is acting. When only V1 is acting, means only V1 is working. Only this V1 is working, means I1 is nullified, neglected, not considered, right? And I3 double dash is equal to I3 when, yes, only, yes, when only, come on, I1 is acting. I1 source is acting. So the statement is the response. See, there are many things to learn from the statement. Learn the statement carefully. I taken the statement so not to waste our time. That is in any linear bilateral network. Yes, the network must be linear. Superposition theorem is applicable only for linear networks, right? Let's read the statement. In any bilateral, any linear and bilateral network or circuit having multiple independent sources, the response of an element will be equal to algebraic sum of the responses of that element by considering one source at a time. Beautiful statement. But the network must be linear and bilateral. And one point I want to tell you here, that is you cannot find power directly. I repeat, you can find voltages, currents directly with the application of superposition, but you cannot find the power directly with the application of superposition. Why? Because power is non-linear. Why? Because power is I square into R or V square by R. I square, yes, it is non-linear. It is non-linear, right? What is a linear circuit, sir, or linear element, sir? The element which satisfies both superposition and homogeneity is called as linear. Please make a note of these points, very, very important. See, HPCL fellows will ask questions on these statements only. Mostly they are going to concentrate on theory questions or simple questions having some twist, right? Most of the people won't concentrate on the statement, but statement is very, very important. In a linear or any linear bilateral, what is a bilateral element? If this element conducts equally on both sides, means suppose if this is A, this is B, you are connecting battery positive terminal to A, negative terminal to B, and it is conducting. Now I'm reversing the element, I'm keeping the battery same, means B is connected here, A is connected here, means though you are reversing the connections for that element, if it is connecting equally on both sides, then that element is said to be bilateral element. What are the examples of bilateral elements? Are resistance, inductance, and capacitance. All three are perfectly bilateral, right? And what are the linear elements? Are ideal RLC elements are linear. Ideal RLC elements are linear, right? Yeah. In any linear and bilateral network or the circuit having multiple independent sources, yes, for example, say I taken two, that is, if there are, it is having two sources, then the response of an element, yes, I taken this response, the current in the R3 I taken it as I3, that is element will be equal to the algebraic sum of the responses of the element by considering one source at a time. Yeah, here first I considered V1, I got I3 dash. Second I considered I1, I got I3 double dash. That I3 dash plus I3 double dash will be total current I3, right? So this is the statement of superposition theorem. Yes, superposition theorem. And superposition theorem is applicable with dependent sources also, but you should not count the number of dependent sources. You should not count the number of dependent sources. Suppose if it is having three independent sources and one dependent source, the number of subcircuits, yes, this kind of question, yes, so this kind of questions may be possible. The number of subcircuits using superposition theorem are dash, that is equal to number of independent sources only. Because without independent sources, dependent sources cannot perform or cannot supply the power in the circuit. Therefore we should not consider dependent sources as sources to apply superposition theorem. The number of subcircuits in the superposition theorem is equal to number of independent sources only, right? Number of independent sources only. Yes, please type in the chat box if you have any questions. If you have any questions, you can type in the chat box, right? Yes, yes, fine. The next theorem I'm going with is Thevenin's theorem. Yes, one of the very, very important theorem, Thevenin's theorem. This Thevenin's theorem is also applicable for linear bilateral circuit only. For non-linear circuits, this Thevenin's theorem is also not applicable. What this fellow says is, suppose if you have a complex network, very big network, like see, for example, let me take I have resistance, I have voltage source here, I have current source here, and after that I have resistance, I have some or yeah, let's not take dependent sources now, it may be complicated, resistances like this. Now with respect to this A and B, see, this is very complex network now, it's very big network. This total can be represented as one single voltage source with one single resistance, and this is A, this is B, this is called as Thevenin's resistance R Thevenin, this is called as Thevenin's voltage V Thevenin, right? So any complex linear bilateral network will be represented with a single voltage in series with its resistance. That voltage is called as Thevenin's voltage and resistance is called as Thevenin's resistance. Read the statement. Thevenin's theorem states that any linear circuit containing several voltage sources and resistances, maybe voltage sources and current sources also, so several current sources also, need not to be always voltage sources, and resistances can be simplified to a Thevenin's equivalent circuit with a single voltage source and resistance connected in series with load. Yeah, here you are going to connect the load. Suppose here I am connecting some load, R load, the same R load is connected here, means at what branches, at what terminals you want to observe the Thevenin's equivalent, there what are the load that is there, load resistance, you remove it, then total circuit you get in this form, then you are going to connect it. This is Thevenin's theorem. Next theorem is Norton's theorem. Norton's theorem. Norton's theorem is also similar to Thevenin's theorem, but in Norton's theorem, what we do is we are going to represent entire complex. So this, for this one also, your circuit must be linear and bilateral. So this is I Norton, and this is R Norton, and this is A, and this is B, and this is A, this is B, and we are going to connect here load resistance. We are going to connect here load resistance, right? Read it. Norton's theorem states that any complex linear circuit can be simplified to an equivalent simple circuit with a single current source in parallel with a single resistance connected to the load. This is my load. Yes, that is Norton's theorem. Norton's theorem is also applicable for linear bilateral networks only, right? That is about Norton's theorem. Then we have, yes, reciprocity theorem and Tailor's theorem. Reciprocity and Tailor's theorem. And a substitution theorem is not there in the syllabus. And we have maximum power transfer theorem also. Yes, MPT, one of the very, very important theorem. Let's understand the statement of reciprocity theorem. What that fellow says is the reciprocity theorem says that in any linear bilateral network, you see, reciprocity theorem is also applicable for linear bilateral networks only. Yes, or circuit with one independent source. Yes, if you want to apply reciprocity theorem, yes, there should be only one independent source, not multiple independent sources. The response to the excitation stays the same even if you swap the source from the input to the output terminals. Means even though you are changing the positions of source and load, that the source to response excitation is going to remain same. That is given by reciprocity theorem. Yes, see, the circuit must be linear, circuit must be bilateral, then there is source here, there is load here. Now you are getting some ratio of source to response, ratio. Okay, if you are exchanging these two, swapping these two, means in place of source put the load, in place of load you put the source, then you take a ratio of those two, that is going to remain same, right? Yeah. The response to excitation stays the same even if you swap the source from the input and the output terminals, right? Yeah. What is maximum power transfer theorem, MPT? Maximum power, yes, maximum power, yes, transfer theorem. See, this is also applicable for linear bilateral networks only. Maximum power transfer theorem also applicable for linear bilateral networks only. Therefore, what it says is in any linear, yes, linear bilateral, yes, bilateral network or circuit, maximum power will be transferred. Yes, maximum power will be, yes, transferred to load. Yes, transferred to the load, to the load. Yes, if load resistance is equal to Thevenin's resistance of the circuit. What is this, sir? Let me take one simple circuit and tell you. Let me take one simple circuit and I'll tell you. Here, observe, please. Observe. So here there is some circuit like this. There is some circuit. Yes. This is 2 ohms. This is 10 volts, and one more resistance here of 2 ohms. Here I am going to connect some load resistance of RL at the terminals A and B. At the terminals A and B. Now the maximum power that will be transferred to RL will be going to happen if RL is equal to R Thevenin. How to find R Thevenin? I told you, if you want to find R Thevenin, remove the load, sir. Then you stand here. When you are finding any equivalent resistance, all voltage sources must be short circuited and current sources must be open circuited. Now, if you short circuit the current source, that is the voltage source, I repeat, all voltage sources must be short circuited, current sources must be open circuited. If you stand here, if you observe, 10 is short circuited, 2 is in parallel, 2 is 1 ohm. Therefore, load resistance RL is equal to R Thevenin is equal to 1 ohm, right? And if you do this problem, how much is the maximum power that is transferred to the load is, see, P max transferred to the load is equal to V Thevenin square by, yes, V Thevenin square by 4 times of RL you get. 4 times of RL unit. So the efficiency is 50% only. Efficiency is 50%. RTH. In fact, RL is equal to RTH. RL is equal to RTH. The efficiency is 50%. Please do remember this formula also, right? So these are the theorems which are important for us. Those are the theorems which are important for us. Let's go. Let's enter into the problems. Let's enter into the problems, right? Yeah. What is the first problem? The resistors having resistances 50 ohms, 100 ohms, and 150 ohms are star connected to terminals ABC. Okay, that fellow says A, B, C. Let's take it as 50 ohm, and let's take this one as 100 ohm. Yes, let's take this one as 150 ohms. Okay, this is A, this is B, this is C, ABC, right? That fellow given capital ABC, no issues. The resistance of the branch BC of the equivalent delta connection is, he's asking this value. He's asking this value. Direct question, direct question, no twist, nothing, no twist, nothing. So simply RBC is equal to, yes, star to delta sum of the connected elements plus product of the connected elements by opposite. How much it is? 150 plus 100 plus 150 into 100 by 50. So 50 threes it is. So RBC is equal to 400 plus 150, that is 550 ohms. How much it is? 550 ohms. Option is C. Option is C. Let's go to the next question. What is the equivalent resistance between the terminals A and B? So he is asking you to stand at A and B, and he is asking you to find the equivalent resistance. I told you, when you are finding this kind of equivalent resistances, you have to open circuit the current sources and short circuit the voltage sources. Here only one current source is, I am open circuiting it, and I am redrawing the circuit. It is always better to redraw. If you try to do with your imagination, there is a possibility of connecting mistakes. So this is point A, yes, and this is point B. Yes, A to some point, see, A to some point X, how much resistance is there? A to X. A to X, how much is there? 2 ohms. B to X is also 2 ohms is there. 2 ohms. This is 2 ohms. This is 2 ohms. Fine. Now, again, A to Y. A to Y. But this current source, we are open circuiting it. Nah? This current source, we are open circuiting it. Thus, X is not equal to Y. X is not going to be equal to Y. I can say, see, it's better to inspect the current. Yeah. Now, open circuit this one, please. Open circuit it. The current that is flowing in this one, yes, the current in this flowing in this one, all are same. But we are taking, but I can't connect these two. If I open circuit it, if I open circuit this current source, I cannot connect X with Y. X and Y are not same. If it is short circuited, no, then I can connect X with Y. Then I can connect X with Y. So A and B I taken. This is point X. Yes, A to X and B to X, we have some resistance. How much? 2 ohms and 2 ohms. 2 ohms and 2 ohms. A to Y, yes, let's take this point as Y, the same point Y. A to Y, some resistance. How much it is? 4 ohms. Yes. B to Y, there is some resistance, 6 ohms. B to Y, 6 ohms, right? Now we are standing here. And I want this A and B. Now, here, this question framing itself is wrong. The question framing itself is wrong. If this A and B both are same, then I can connect these two directly. These two directly, I can get it. This question framing is wrong. Why? Because as this is a current source, if I open it, this point are not same. Okay. Let's go to the next question, please. That question, you leave it. That question framing is wrong. Otherwise, why? Because it's not converging. You see, we have two different points. I can say this point is different from this point. Why? Because we are open circuiting it, and the current here is same. In fact, frankly to speak, all resistance are connected in series. Why? Because if you open circuit this I, I'm talking about after disconnecting the current source I. See, when you are finding equivalent resistances, voltage source must be short circuited, current source must be open circuited. If I open circuit it, yeah. See, I'm stretching the terminals of A. If I'm stretching the terminals of A, let's take this way. B, you take this way, and let's not consider this one. Let's not consider this one. So yeah, you can do like this. This 2 and 2 both are in series. This 4 and 6 both are in series. So we can get like this. Yes, we can get like this. RAB. This 2 and 2 both are in series. That 4 is in parallel with 6 and 4 in series. That is 10. 4 in parallel with 10 is 4 into 10 by 4 plus 10 is 14, right? R1 R2 by R1 plus R2. So 40 divided by 14 is the answer. Yes, yes, it got converged. See, just take it up, and leave this one, then these two are in series. Okay, these two are in series. This 2 ohm, this 2 ohm are in series. Yes, yeah, if you observe, yes, yes, we got, yes, yes, this diagram is correct only, it is converging, man, it is converging. Yeah, you see these two are in series. 2 ohms are in series. Yeah, this is point y, let it be y, if you want me to redraw. Yeah, I drawn the diagram correctly, but I did not connect it. Yeah, so I'm going to get like, this is point A, sorry, this is point A, this is point B. Yes, between these two are in series. To the A, to the B, this side both are, this is 10 ohms, this side it is how much, 4 ohms. 10 into 4 by 10 plus 4. Yes, 10 into 4 by 10 plus 4, how much it is? Yes, anyone, good question. So in the initial stages, we feel like it is not converging, but if you just observe closely, we get how much it is. 40 divided by 14, it is 2.85. Very good question. 2.85 ohms. The option is B. The option is B. 2.85 only. No, 2.857 I got. 2.86. You see, this calculation is also how much important here. You see, calculation is also how much important. You see. Okay, do not commit any mistake in the calculation, please. Right? Good question, please. Next question. Superposition theorem requires as many circuits to be solved as there are, I told you, equal to number of independent sources, right? Yes, sources, nodes, sources plus nodes, plus measures, nothing. Sources, that too only independent. We should not consider the number of dependent sources as sources when we are going for superposition. Next question, please. Teligans theorem. Yeah, what Teligans theorem says? Teligans theorem says that total power, how much power is given, that is equal to taken. The total power given is equal to total power loss plus total power taken. Means law of conservation of power. This Teligans theorem is going to be verify. So this Teligans theorem is applicable for both linear, non-linear. For any circuit, Teligans theorem has to applicable. Why? Because it is just checking law of conservation of power or law of conservation of energy. Right? Please do keep in your mind, Teligans theorem verifies law of conservation of power or law of conservation of energy. Right? Teligans theorem is applicable to linear networks only, non-linear networks only, linear and non-linear networks only, linear, non-linear, passive or active on time. Whatever it is, Teligans theorem must be applicable. Whatever it is, Teligans theorem must be applicable. Why? Because it is verifying law of conservation of power. It is verifying law of conservation of power. Right? Yeah. Next question, please. Next question. A system is linear if and only if it satisfies both superposition and homogeneity. Option A is principle of superposition. Option B is principle of homogeneity. Yes, both A and B. Yes. See, an element is said to be linear, or a system is said to be linear if it is satisfying both superposition and homogeneity. Right? The next question, please. The Norton's resistance of the circuit shown below is means you have to stand here. This is the Norton's resistance. You are observing from here. I told you, when you are going to find the equivalent resistance, Norton's resistance and Thevenin's resistance, in fact, both are same. R Norton's is equal to R Thevenin's. When you are finding at what terminals it is required to find, you go there and stand there, and you open circuit the current sources and short circuit the voltage sources. Then rather equivalent circuit, then what you are going to get, this 4 ohms, this 12 ohms, and after this 12 ohms. This is A, this is B. 12, this is 12. No, it is 1 ohm, sorry, 1 ohm, it is not 12. This is 1 ohm, this is 4 ohm, this is 12. This 4 and 12 are in parallel, so RAB is equal to 4 in parallel with the 12 plus 1. So RAB is equal to 4 into 12 by 4 plus 12, 16 plus 1. So 4 cities, 3 cities. So RAB is equal to 4 ohm. Simply, the option is C. Option is C. Norton's resistance. See, Definitely one question from the area of theorems in your HPCL examination, and that fellow is not going to in depth, not going to test your concepts in depth. What I'm discussing are more than enough for your HPCL examination. Okay, let's go for the next question. Yeah, maximum power transfer theorem states an independent voltage source in series with an impedance Z Thevenin delivers maximum average power to the load impedance when ZL is equal to. I told you about maximum power transfer theorem in DC, that is R load must be equal to R Thevenin for maximum power transfer, but for AC, Z load must be equal to Z Thevenin conjugate. Suppose if this Z load is inductive, means if Z Thevenin is inductive, Z load must be capacitive. If Z Thevenin is capacitive, Z load must be inductive, right? So this is the condition. Please do remember for maximum power transfer theorem, that is Z load is equal to Z Thevenin conjugate. Option is C. Option is C. Direct question it is. Next step. Assume that the source in the circuit shown here is delivering maximum power to the load. If it is deriving maximum, it is driving maximum power to the load, RL must be equal to R Thevenin, that is equal to 10 ohm, right? Yeah, that fellow said that assume that it is delivering maximum power. If it is delivering maximum power, load resistance must be equal to source resistance or Thevenin's resistance. So R load is equal to 10 ohm. Then maximum power to load resistor. What is the total power? Yes, if it is also equal to 10 ohm, how much is the current? Current I is equal to 10 divided by 10 plus 10. Current is 0.5. Therefore, total power is asking. Total power means this is voltage V. 10 into current is 0.5. That is 5 watts. Yeah. In the last session, I told you how to find the power. In the last session, I told you how to find the power, right? Yes or not? So answer is 5 watts. Option is A. Option is A, right? Next, superposition theorem is valid for only for linear circuits. Yes, superposition theorem is valid only for linear circuits. If it is non-linear, yes, we can't do anything. And you may be confused with the option D, circuits with active elements. Yeah, some active elements are non-linear. Suppose if you take BJT or operational amplifiers, those are active elements, but still they are non-linear. You can't apply superposition, right? Next question, please. Norton's theorem, when applied to DC circuit, results in, yeah, what a Norton circuit is. A current source in parallel with the resistance. Norton's current in parallel with the Norton's resistance. Current source alone, voltage source alone, a current source with a resistance in parallel. Option is C. So all these questions are previously asked PSU questions. So these are not my own questions. These are the questions asked previously, right? Yes. Let's go for the next question. The maximum power is delivered from a source to the load when the source resistance is, yeah, here very good question. This is very good question. So here source resistance is variable. You see, this is source resistance, this is load resistance. If you want maximum power transfer to the load, then source resistance must be equal to 0. We are fixing this one. So previously my variable is load resistance. Whenever load resistance is variable, my load resistance must be equal to source resistance is the condition. In AC, load impedance must be conjugate of Thevenin's impedance in AC. But here load resistance is fixed and source resistance is variable. Then source resistance must be equal to 0 for maximum power transfer to the load, equal to 0. Why? Because how much less this is, that much very happy. If it is 0, in fact, total power, total current, total power is going to the load only. No power is going to lost in the source resistance, right? Next question. When a circuit is represented by equivalent Thevenin circuit and Norton's circuit, I can say Norton's resistance is equal to Thevenin's resistance. I already told you, that is the direct question. As I'm saying, these are the previously asked PSU questions. Like you can take a previously asked examination of SAIL, Steel Authority of India Limited, or some state PSUs, or SSC JE, or HPCL. From different PSUs, I collected these questions which were asked. This is the level. See, don't think that I'm teaching very simple questions. These are the level of the questions that were asked in previous PSU examinations. Next question, please. Yeah, to find current in a resistance connected in a network, the Thevenin's theorem is used VTH RTH. Yeah, that fellow given RTH. How much it is? RTH is 5 ohm and VTH is 20. Yes, VTH is 20 volts. Yes, that fellow says VTH is 20 volts. Yes, what is asking? The current through the resistance is the current, okay, to find the current in a resistance in a network, in a network, but this fellow did not given. Okay, options, let us see. See here, this fellow connected load, this fellow connected load, this is R load, R load. See, whatever may be the value of R load is asking if the current. So current I is equal to 20 divided by 5 plus RL. This RL anyhow positive. RL is anyhow positive. There is no question like RL is going to be negative. There is no question like RL is going to be negative. See, see 5 plus something, definitely I is equal to 20 by greater than 5, then definitely I is less than 4 amperes. If if RL is equal to 0, then I is going to be 4 amperes, but RL is greater than 0 means a positive value, therefore it is less than 4 amperes. See, less than 4 amperes. Without looking at the options, if you see the question itself, no, it feels like insufficient data. Yes, truly it is insufficient, but if you look at the options, yes, it is sufficient, right? Next question, please. The Thevenin's theorem to find ZTH means he is asking us to find the Thevenin's impedance, ZTH. Yeah, all dependent current sources are short circuited and independent all independent current sources are short circuited and independent voltage sources are open circuited. No, 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 no. What I told, if you want to find Thevenin's equivalent impedance or resistance, whatever it is, you must short the voltage sources. I told you why you have to short. Means I have to nullify voltage source. Voltage is nullified means voltage is 0. 0 voltage means short circuited. Nullify the current source means current is 0. Current is 0 in open circuit. Option A is wrong. All independent voltage sources and current sources are open circuited. No. All independent voltage and current sources are short circuited. No. All independent voltage sources are short circuited and all independent current sources are open circuited. Option D is perfectly suitable for the given question. Yes, yes, it is. Open circuit the current sources, short circuit the voltage sources, right? So again, I'm repeating the same statement. That is, all these are the previously asked PSU questions, right? So if Norton's method is applied to find the current in the resistance RL as shown in figure, the Norton's equivalent current in the resistance RL will be. So simply he's asking, yeah, he's asking here means in RL means he's asking what is the Norton's equivalent circuit with respect to this point A and B. With respect to this point A and B. So wherever you want to find, remove that load, I told you, remove that load. Then how much is the current? 25 minus 5, that is 20. 20 divided by 4. 20 divided by 4 is 5. Yes. But okay, sorry. Norton's means a short circuit. Nah? Norton's current means short circuit current. ISC. This is, if you want to find Norton's current, VOC. See, V Thevenin is nothing but VOC, open circuit voltage. I Norton's is nothing but ISC, short circuit current. So what I did is I short circuited this. Therefore, I'm going to get ISC. Now you find 25 divided by 2. How much it is? 12.5. So ISC, that is equal to I Norton's is equal to 12.5 plus 5 divided by 2, that is 2.5. So how much it is? Total 15 amperes of current. And when you're finding Thevenin's equivalent resistance or Norton's equivalent resistances, then you open circuit that load resistance. Means I remove that load resistance, and in the place of load resistance I'm standing. And I told you, when you're finding resistance, short circuit the voltage sources and open circuit the current sources. If I short this one, this is 2 ohms, this is 2 ohms. 2 ohms, 2 ohms, both are in parallel. I'm going to get R Norton's is equal to simply 1 ohm. How much it is? R Norton's is 1 ohm. Therefore, ISC is 15 amperes and 1 ohm. Yes, 15 amperes and 1 ohm respectively. 15 amperes and 1 ohm respectively, right? That is very, very easy question. If you want me to draw its diagram, I'll draw it and explain very clearly. As it is very simple one, directly I explained. See, first of all, find R Norton's. When you are finding Norton's resistance, I'm taking the total circuit. I'm taking the total circuit. Yes, this way. We are here. First of all, load resistance should be removed. Load resistance we removed. You stand here. Short the voltage source. Short the voltage source. This is 2 ohms. This is 2 ohms. Take that A and B. Yes, if you draw with respect to A and B, this is point A, this is point B. You can get both the resistances in parallel. 2 in parallel with 2. So RAB, that is equal to R Norton's, is equal to 1 ohm simply. 1 ohm it is simply, right? So this way we have to find Norton's equivalent resistance or Thevenin's equivalent resistance, right? If you want Norton's current, no, short circuit it, short circuit it, short circuit it. This is 25, this is 5. You see, What are the current that will go here? Current always choose a short path, that current will come and go here. Just I am applying Ohm's law. How much is the current here? 25 divided by 2. How much is the current here? 5 divided by 2. So 12.5 plus 2.5 will be simply 15 amperes. Will be simply 15 amperes. So this is how you have to prepare for your networks syllabus for your HPCL examination. Not only for HPCL, for all kinds of PSUs, this kind of questions only will be asked. If you want the PDF copy of this notes, please message me to this number 891-9999-705. Right, YourPedia started its module for, I can say, at this HPCL straight away tailor-made module, which is result oriented. I can say result oriented, completely in the way of HPCL preparation. Okay, so we are not going to take up unnecessary things, unnecessary derivations. We are not going to waste your valuable time. Completely in the direction of HPCL we are teaching. If any one of you interested, you can call on the same number. Thank you.